as I told you, that in Lex file, you will be getting three different sections. And three different sections are having their own utilization. Okay. So this Lex tool is divided into three different sections, and each sections is being delimited or given boundaries using this modulo or percentage sign. So the first section is called declaration section. Okay. So that means you can see here all the hash including means header files, all the variables. Yeah. If you are having any function prototypes, so every details related to your declarations which you want your compiler should know prior. Okay, so all these declarations or those variable informations which you declare prior its usage, so that you utilize in your first section. So you keep all this information in your first section of your Lex input file. Next section is for your rules and function writings. So rules means the transition rules. As I told you that you will specify your tokens using regular expressions, and you will recognize them using finite automata. So that means there exist some rules. So what are the rules which will be applicable? Suppose you have written some scanf statements, suppose, okay, or you have written some printf statements. So that means you want something to be printed. Huh? You want some inputs to be taken, right? So these are some functions you need to perform when you are executing that particular program. Okay, so what are the rules or what are the transitions that are going to occur when this program will run? So that actions, that set of operations, you need to mention in the second section, where you have seen that scanf and printf and everything is written in the second bracket. Okay, curly braces. Okay, so that means the actions which you need to perform when particular pattern is understood or they are being recognized, then particular these transition rules should be performed. Okay, so those transition rules you will mention along with its action. You will mention in the second section. Okay. Now the third section is the auxiliary procedure. So this auxiliary procedure is basically is responsible for calling some of the inbuilt function of your Lex files, Lex utility program. Like you have seen here, YY Lex is a function that is written. Okay, so basically, what is the procedure this lexical tool is following? It is taking your source program. Okay, that Lex compiler is taking your source program and is generating an output which is called lex.yy.c file. It is output is lex.yy.c file. Okay. Now your C compiler is taking that lex.yy.c file as an input and is generating the output as a.out. Okay, so that means when it is generating that output or when it is taking out that output, so that is comprises of all the streams of tokens that lexical analyzer has separately gathered from your source code. Okay. So this file format generally comes in your exam. So short note may also come. So apart from YY-Lex, you may have some other auxiliary functions available in this Lex programming utility called YY-Wrap, then YY-Less, then YY-More. So these are having some specific functionality that you will come later on. That you will come to know about all these details later on. Okay. So, and this is a tool which is used in the next phase. So that means after your lexical analysis, you have your parser phase or syntax analysis phase. There, this parser tool is used. So some general information about that tool is also given, like why this YY parser tool is used and what its job. So, and why these two tools information are needed here? Because I told that your lexical analyzer phase and your syntax analyzer phase works hand in hand. So both are working hand in hand one is generating the output and another is taking the output. So this is a continuous process. Okay. So the Lex tool and YY parser tools are also working hand in hand. Okay. So what this YSCC parser generator tool, what it is doing? So input is specified to this parser. So either that input will give in the form of a context-free grammar or in the form of a Chomsky normal form. Okay, so I will give you the examples that how to write a grammar rule, and that grammar rule should be feeded to the parser. Either it is a top-down parser or it is a bottom-up parser, doesn't matter. But you have to specify your input using those grammar rules. Okay, so it's this parser will generate an output as a parse tree. So a tree-like structure it will try to generate. So for this YACC, it generates a C function which is stored in a y.tab.c. Okay. So this is a C file where actually the output generation will take place. And for generating that output, the information which it needs that will be supplied by your Lex tool. That means the stream of tokens. Now, what the function this YSCC parser tool is using for doing or for completing your parsing process? So it uses the function called YY parse function. Okay, this parse function is internally calling this YY lex function, which your lexical analyzer tool has used for generating the stream of tokens. So both these tools utilize these auxiliary functions which is available, and they work hand in hand for completing the syntax analysis phase up to that phase. Okay, so they compile these functions to obtain the compiler, because after generation of these files, the C compiler will generate the out file. Okay, so if see here, as I told you, you have a Lex source, you have a YACC source. This Lex source is acting on the lexical analysis phase, and YACC source is acting in the syntax analysis. But you can see here that they both are acting hand in hand. So that is why this parallel, they are doing their job. So once this output it has got from the lexical analysis phase, it is taking as an input. Right. So the Lex source is generating this lex.yy.c file, and this is the input for your YACC parser. So it is taking this as one of the input, and other than that, it has its own YACC source where the rules and every other grammar related informations are stored. So with the help of this both input, it is storing them in this y.tab.c file and is generating this a.out file. Okay. So this your input source file is similar to your Lex input file, where your declarations, your rules, and your subroutines information, every parts related to your source is stored. Okay, so basically there are 4 parts of your output generation. That what are the operation involved, and in that operation, whether you require both the operands, that means your left operand or right operand, and what is the output it is going to generate. Because if it means the parse tree doesn't get all this information, then that parse tree generation will be incomplete. Okay, so that means a particular node which is having its both left child and right child, so it should be completed. Otherwise, that parse tree generation will be thought as an incomplete operation. So in that case, the syntax error will be generated. Okay. So your YACC parser requires every information of these 4 parts for each of the operations user has mentioned. Now talking about the cross compilation. So cross compiler I have already told that in a cross compiler, you try to build a compiler which is capable of creating an executable code for a platform other than on which that compiler is run. So I told you that the originator machine and the target machine where that compiler will be executing, both the machines are different in case of your cross compilation. So you will build a compiler having such capabilities. That means the platform where you are going to run that compiler, that will be different where you have created. Okay, so both the platforms are different. So that means both the OS, both the architectures can be different. So, so you will create if you can create such kind of compilation scenario and environment, then your compiler will be treated as a cross compiler. Okay. So these cross compiler tools are mainly used to generate the executable for your embedded systems or such systems which require multiple platforms to be executed. Okay. So it is used to compile for a platform upon which it is not feasible to do the compilation. So that means the embedded system. So in that case, what happens, like in case of a automatic washing machine. So you can think that in a washing machine, you do not have such resources to execute those compilers, right? So what you do, you put or you insert the the compiled code into that particular machine or particular platform, because in that platform or in that particular device, you do not have that environment to run your codes. Okay, so it is not feasible to run that particular compiler code into that particular device. So after compilation, you can feed that for getting its output. Okay. So in that case, some devices which are mainly used in microcontrollers, okay, or some machines which actually does not support any kind of operating system environment. So in that case also, you need some kind of output, and for that you need some kind of compiler to be executed before generating its output. So such scenarios you may have to develop cross compilation technique. Okay, where you will target your target machine will only execute that. Okay, but other than that, the origination of your compilation and the compilation process and every checking and other thing which we have discussed, that is completed in its originator machine. Okay, so this cross compilation is used in such kind of scenarios. Like here, you can see some of the examples, like in embedded computers, in microwave ovens, as I told, some washing machines, some environment where these microcontrollers are operating and it is generating some of the outputs, and where the testing and debugging is not possible because such resources are not available in those embedded systems. So prior to putting those codes into such devices, you create one other originator machine where every compilation related things are done. So you are only going to execute that in the target machine, target embedded system. So there your cross compilation nature is useful. Okay. So and these are some of the examples. So you go through it. These PPTs. You will come. Next, we will come to the next one of the previous number. Not this one. Okay, so we'll start today with a fresh chapter, which is the first phase. That means lexical analysis phase. Because till now, whatever I have taught about the compiler basics. I have taught about its utility. I have talked about the briefing about different phases and how every phase is giving output to its next phase. And what are its cousins, like a compiler is having other modules also associated with it, like linker, loader, assembler. Okay, so all these things we have talked so far. Okay, today we'll start with the next first phase. That means the lexical analysis phase here. Okay, so here basically what we have to read, we have to understand that what are the main tasks of your lexical analyzer. Not only scanning, but other task is also there, and how when it will specify each token. So how it will specify each token. Okay. Now after specification of token is done, how it will recognize each token. Because if it is not able to recognize each token, then definitely it will not be able to store its information in the symbol table. And if its information is not in the symbol table, then subsequent phases will be improper because they require the information of every symbols present in your source code. Okay. next we will talk about this lexical analyzer generator tool, Lex tool. And for recognition of tokens, we need some knowledge about finite automata also. So that also we will see. And this design of lexical analyzer tool, we just discussed now the every three parts of your Lex tool. So that also we will see in this lecture. So by this diagram, you can easily see that how these two phases, that means lexical analysis phase and its next phase, which is known as syntax analysis phase or parsing phase, how these two phases work hand in hand. Though they are kept separated, and why these two phases are kept separated, why they are not clubbed together, that also I have discussed yesterday. Okay, but from here, from this picture, you can see that this is a continuous process, that your lexical analyzer will generate the token and will pass this on to its next phase called parser, and parser will do some kind of analysis or will try to create the parse tree according to the token it has collected. Okay, and this process is a continuous process. So whenever the parser needs the next token, it will ask the lexical analyzer to provide them. Okay, but both these phases takes the help of the symbol table, because each and every symbol is necessary. Okay, and whether this symbols informations are written correctly or written incompletely, that is also equally needed. Okay, so before checking each and every symbol and before checking the grammars, the parser needs to have that information from the symbol table. So that is why both need the symbol table equally. And then when the parser is successful in generation of your parse tree, then parser will generate its output as a parse tree and will send that to semantic analysis phase or its next phase, which is the syntax related transmission. So why these two phases are working hand in hand, but still we need to separate them? This I have already told that because we want a simplified design. So for sake of your simplicity and for developing or improving the compiler's efficiency and enhancement of your compiler's portability, keeping in these things in your mind, you have segregated these two phases separately. You have kept lexical analysis phase separately, and after that you have kept for grammar checking and for rule checking, you have kept your parsing phase or syntax analysis phase. Okay. Now, we are talking for 2 or 3 days about tokens, and tokens. So what are these tokens? So in technically, if I talk about token, so your token is, a token can be a single token or it can be a pair of token, okay, or a collection of token. That is also possible. So your token is a kind of a collection, you can say, a collection where actually you are forming that collection and you are trying to draw a meaning out of it or pattern out of it, or rather I can say in a simplified version that when you are selecting some of the collection of your character, so either that may create an identifier or that may create a keyword or that may create any function name, any other symbol it can represent. So a kind of representation you are trying to make. Okay, so for this, the smallest unit, suppose a character or a number or a special character, whichever you are utilizing, those are treated as lexemes. Okay, so lexemes are basically the smallest unit of your words or of your program. Like you are writing if statement, you are writing any suppose any control statement. So you are writing if. So I and F both are forming this keyword. Both are forming this keyword called if. Similarly, for you are writing or else you are writing. So when these lexemes are related or they are creating a set, like suppose if, else, for, these are creating a set. So then that set of related lexemes are called tokens. Okay, so that means a keyword is having a collection of all such of keywords which are allowed in your C language, or suppose identifiers you have collected in your source program. So that is forming a set. So that set of identifiers is a token. Okay, set of operators, suppose you have written, or punctuation marks you have written. So these sets are different tokens for your compiler. Okay, so lexemes are your smallest logical unit by which you are forming a set element of your token, I mean token set element, and when you're obtaining that set, that you are treating as a token. Okay. Now what is pattern then? So pattern means it's a way of describing your token. So that is can be a formal way, can be informal way. So that means by some rules or by some methodologies, you are creating a pattern. The pattern means you are giving a description. So just wait for a second. So pattern means you are basically trying to form a kind of description. So description means how compiler will understand that when I'm writing IN followed by T, so it's a keyword. But when I'm writing this INT, the same characters I am using, but in different fashion. T, then I, then N. So it is tin. Tin is not a keyword, though the same characters are present. So that means some patterns are already, which are stored patterns. Okay, so whichever are stored patterns, that this compiler is treating as a keyword, right? For suppose writing, I'm writing if. So I will write I first, then F. Okay, followed by F. I followed by F. So when it is taking these two characters in this sequence or in this order, then it is identifying it as a keyword, because if is a keyword in C language or C++ language or Java language. But when the same I and F, you are not writing in this order, you are writing F and I. So phi can be any variable name given by you. So the pattern is not matching with the one which is stored in case of your keyword stock of one, right? So that means the description you are creating, and some description you are creating and is storing into the compiler's database. And when the compiler is checking with that grammar and rule set and everything, then it is matching with that stored description or stored pattern. If it comes to know from its stored pattern, then it is recognizing it as a keyword. And if it is not, then it is recognizing it as a identifier which is written by the user. Okay, so that means this token, lexeme, and pattern, these three things are clear to all of you. Token means you are trying to create a set of related lexemes, and lexemes means it is the smallest logical unit by which you are planning to describe your token set, and the description and the way of your description is your pattern, how you're describing your lexemes, okay, and you're trying to form a token out of it. So that is your pattern. So this is nothing but a formal or informal description of your token. Okay. So, so that means every token which it is segregating from other token, so everybody's token attributes will be different. Okay. And that information you have to keep in your symbol table, because otherwise every token is different from other token, that you will not be able to segregate. Okay, so these informations you need because this comes in your questions. So here one example you can see that every token it has collected written in your program, and its informal description and its sample lexemes are kept. Okay. So Now talking about, as I was telling, that whenever it is collecting some tokens, its related attribute information is also that much necessary. So suppose a user has written a line E equal to MC square. Okay. So in this, E is one separate token, equal to is another, capital M is another, then asterisk is another token, C is another token, then double asterisk is another token, and then 2 is another token. So every token, for every token in your angular brackets, it has kept every its attribute information, that which one is identifier, which one is operator, which one is multiplication operator, which one is assignment operator, which one is exponential operator, which one is a number constant, so on and so forth. Okay. So this is according to my line, which is written in the slide. So whatever line you write, so accordingly your compiler also describes, and according to its description, it stores every its attribute information in the symbol table. So in your lexical analysis phase, what basic task your lexical analyzer is doing? So it is not only scanning your source code, but means not only generating from source code to token, it does some additional task also. Like it strips out your unnecessary white spaces written in your source code. It removes the comment lines, because some of the lines we give in double slash, no, for our clear understanding. So these are treated as a comment line. So does lexical analyzer scans them also? No, they do not scan the comment lines. So stripping out the unnecessary white spaces, removing the comment lines from your compilation process, and then keeping track of the line numbers, because as I told you, that it will scan line by line, and in each line character by character. Okay, so it needs that tracking, that where it has already scanned and up to which point it has reached, and what is its next character which is it is going to read. Okay, so it needs to keep track of the line numbers as well. Okay, so when it is keeping track of the line number while scanning the new line characters, your error can generate, okay, in each line. So in which line your error has generated, for that line, for that particular type of error, it will have to generate the error message. Okay, not for other lines. Okay, so error handler is one of the module that we have already seen, that is responsible for storing all such errors. Okay, so whatever lexical analysis phase gets any error while doing all these tasks, so that means pre-processing of macros, that is also a task of your lexical analysis phase, because I told that before compilation only your pre-processing needs to be done. So expansion of your macros, then header files resolving. So everything, every pre-processing task. So that is also task of your lexical analysis phase. So in any of these cases, if any error generates, whichever task I have mentioned, if any error generates, then this is a task of your lexical analyzer phase to generate a corresponding error for those. Okay, so some of the errors I have mentioned here, like some errors are out of your power of your lexical analyzer phase to recognize. Like suppose if you have written some function called fi. Okay, so inside your fi, you have written some variable name or identifier name a is equal to f of x. Okay. So this fi is a printing mistake, or is it really a function, user defined function? Okay, so these are not in the hand of a lexical analyzer phase, because lexical analyzer phase will treat this fi as a function name, because it is not matching with any of the your keyword. It's not a if, so it's not matching with that if pattern. So definitely it will treat this fi as a function name, but that function name's prototype is not mentioned, and inside that function you are trying to check the equality of the operator. So that means you are trying to find out a is whatever the value of a, is it really equal to the value which is returned from the function fx or not. So that fx function, what it is going to return, it doesn't know about that functionality fx. So these are some out of scope work for your lexical analysis phase. Okay. So in that case, if it doesn't able to resolve, so it can generate an error. In fact, suppose some of the lines you have written like this, that d equal to 2r. So in this case, you are trying to assign some value by performing some of the multiplication operation at the right hand side of your assignment document. So once you are ready with your r, then you will multiply that with 2, and then that will be an initialization for your variable d. Okay, so it is not able to recognize such type of errors. Though this is not a problematic area, you can easily do that because this is a formula. Okay, but whether that r will be available or not, whether that r is having some initialized value or not, so you do not know prior, right? So these are some out of scope areas for your lexical analyzer, because lexical analysis phase is a very simple phase. So whatever token it is really it is recognizing, so that information it is storing in the symbol table along with its attribute values. But apart from that, if any further computations required, any further function calling required, so that is not a task of a lexical analysis phase. So for that, it supplies that immediately to its next phase. That means syntax analysis. So that is why the diagram is showing that both these phases work hand in hand. Okay. So such errors are recognized when no pattern for tokens matches the character sequence, as I told you. So such type of lines are not having any predefined pattern. Okay. So if that is not stored in the compiler's database, then how can it tell that this is a valid line or this is a valid token? Okay. So definitely then each of them will be treated as a new identifier, but it may not be the case. Okay. So in that case, from this lexical analysis phase, whatever error it has generated, sometimes it requires that recovery from those errors. So how that error recovery is done? So you have a panic mode. So panic mode means if suppose successive characters are ignored until when it reaches to a well-formed token. So successive characters are ignored means suppose side by side characters it is reading but not interpreting any meaning out of it until when it will interpret its meaning, until it will reach to a well-formed token. Suppose it has taken I, it is ignoring, so it is storing it. Then it has got N, so it is storing it. If it gets T after N, then it will treat it as a identifier. Otherwise, it will treat, suppose it has got IN, then P. So INP is not a keyword, right? So it is not a well-formed token. It is an identifier. So it will put that in the set of identifiers token. Okay. Sometimes it may happen that you have to delete one character from the remaining input. So in that case, it will say that this is an extra thing which you have put in your source code. So if you remove INT and suppose after that you have written a P extra by mistakenly. Okay. So it will give you a clue that remove that P because it is not matching with the keyword called int. Okay. So in that case, the lexical analyzer, the modern lexical analyzer will delete that character from that remaining input so that it can match with the well-formed token. And sometimes it can do the opposite. It may give you a clue to insert some missing character present in your remaining input. So if you insert that particular character there, then it will be a well-formed token. So in that case, it can give you a clue to insert that missing character. Similarly, it can replace some character by another character. So in that clue also it can give you. So sometimes it can transpose two adjacent characters, means swap these two characters. So these are some of the methodologies which your lexical analyzer can opt when it is trying to do some kind of error recovery. Okay. Now, when it is collecting the tokens, so definitely then it is reading each and every tokens character by character. So for that, it needs some storage, right? So that is called buffer. Okay. So you can see from here the E equal to MC square, which you have seen in your 2-3 slides back. So that line, how it is storing. So it is storing in a buffer. So buffer means here an array where all these source codes tokens information will be kept in each cells of your array. Okay. So how it will store? Obviously, character by character, it will store in your buffers. So for storing these characters written in your source language construct, either it require one buffer or it may require two buffers. So basically, these are two schemes, okay, for storing the informations. So when the question may come that these two buffering methods are why required. Okay, one is called one buffer scheme and another is called two buffer scheme. So why these two buffer schemes are required to handle these scenarios? Why not one? Okay, so the question or the answer to that question is that if you utilize one buffer scheme, there you are only having one buffer to store your characters. Okay, and in your two buffer scheme, you have two, or rather, I should say that you have a pair of buffers available to store the characters. Okay. Now, the way it is showing that you have every characters available, you are putting into the buffer. Okay, like E you have got, so you have kept in one cell. Then you have given a space. So space for space, another cell is there. Then equal to, then again a space, another cell. Then M, then asterisk, then C, then your exponential operator, then 2. Then at the last, it is showing EOF, that means end of your input, which is known as a sentinel. Okay, so sentinel means you are putting a marker kind of thing that your line has ended. Okay, so if you are using one buffer scheme, so in that one buffer scheme, you will be using this one buffer for storing the characters. So that these characters where this current, I mean, your tracker is, or the pointer rather, I should say. So you need two different pointers when you are storing these tokens information into the buffers. You need a pointer or a tracker kind of thing, which will tell that what is your current cell that is available in your buffer, and in that cell or in that particular index, what is the character right now who is eligible to be kept. Okay, so for this you need basically two different pointers. So these two different pointers will be responsible for reading and for storing each of the characters present in your token. Okay, so what are these two pointers? These pointers are known as LB and SP. So your LB means lexeme begins. So when you are writing that particular lexeme, so what is its beginning index, and this LB will be responsible for pointing to the beginning of your lexeme. Okay. Now suppose you are writing a keyword, say INT. So your I is your lexeme where your keyword is beginning, and T is your lexeme where your keyword is ending. So what I mean to say, let me draw in the board. Suppose you have a buffer like this. You have many cells in your buffer. I do not know its space, so dot. So this is your buffer where you are planning to store your lexemes. Okay, for lexemes writing, you have one character which is the beginning of your lexeme, and one will be there where the end of your lexeme, right? So suppose you have written int, so your I will be stored here. Okay? So here your LB pointer will point, which is the pointer which is responsible for pointing to the beginning of your lexeme. Then suppose n next character will come. So for that, you have a pointer called SP, which is stack pointer. So it will utilize the stack. Okay, SP. So the stack pointer will move time to time. So that means when you are storing this I, your beginning letter I was only in the buffer. So SP was pointing to that. When the next character has come, so this SP will be moved to next position. So here your SP will come because right now your current character is N. Next, when T will come, your SP will be moved from here to here. Okay. Now when the space will come, so that means before this space, whatever is between your LB and SP, it has collected. So that belongs to a single token. Single token. So that may be an identifier, maybe a keyword, maybe an operator, anything, a function name, variable name, constant, anything that can be, but it has to report that what are the characters that it has captured between LB and SP. So definitely SP will stop where the last lexeme letter will remain, and LB is only means keeping the value of your starting point. Okay, so between your starting point and ending point, whatever letters or whatever characters it has collected, that should belong to a single token. Whatever it is type, that I don't mind, but I have collected a single token. So what are the characters which belong to that single token, which is between your LB and point? Okay, so likewise, again, suppose some other token will also come. Suppose int, then space, then I you have written. So for that, again, next token will start. So here again, your LB will come because this is the starting. And for I, it is a single character which we are denoting for an identifier. So SP will again point here and it will stop here itself. Because again, after I, you will get a space. Okay, so this is your second token. Again, you will give a space. So whenever it is getting a space, that means before space, where your SP is pointing, so between your SP and LB, whatever letters you have collected or characters you have collected, that should belong to a single token. Okay, so in your one buffer scheme, basically you utilize this single buffer for storing all your lexeme informations or all your token informations. Am I clear up to this point? Am I clear? If anybody is having any doubt, you can ask me. Any doubt anybody is having? Am I audible or not audible?
Yes, ma'am, audible.
Is it clear up to this point?
Yes, ma'am.
Okay. So in one buffer scheme, you are utilizing only one buffer, and in your two buffer scheme, you are available with an alternative buffer in your memory. So then question comes, ma'am, if this one buffer is enough to do this job of storing this lexeme's information, then why this two buffer has come? So for this, I'm giving you an answer that in your two buffer scheme, what happens? You utilize these buffers alternatively. So whenever your first buffer is full, suppose you are in a way of writing one token's information and that is not yet completed, but your buffer is full. So in that case, where the rest of the information will be kept. So in that case, you will utilize these two buffer scheme because you are available with a alternative buffer with you. So when this first buffer is full, you are starting your lexeme's information in your alternative buffer. And when the second is again full, again you are utilizing your first buffer. So likewise, you are never lack of your memory or lack of your buffer size. Okay, so that is why the boundary conditions, which are actually a problem of your one buffer scheme, that is being resolved when you are utilizing the concept of two buffers. Okay, so these two schemes are basically storing your block of inputs data for buffering purpose, and as you are utilizing these buffers, so basically you are avoiding the costly access of your secondary storage. So that means many times you do not have to store them into the hard disk and again load them from the hard disk. So this costly accessing from your secondary storage each time is not necessary. So once it is done and it is permanently, it should be kept in your hard disk. At that time only you are utilizing or you are storing them in your secondary storage. Other than that, every temporary operations are being done in your buffer level, in your primary storage level. Okay, RAM. Is it okay with everybody? Why these two buffer scheme we are utilizing? Because this comes in your question. That why these two buffer schemes are important than your one buffer scheme. Okay. Any doubt anybody is having? Anyone who is having doubt? You go through these slides. If any doubt persists, then let me know tomorrow. Okay, tomorrow also we are having class. Okay.
ম্যাম পিপিটিটা পাঠিয়ে দিলে ভালো হতো।
আচ্ছা আমি পাঠিয়ে দিচ্ছি, যদিও এগুলো টিসিএস আইনে আছে অলরেডি, বাট আমি পাঠিয়ে দিচ্ছি আমি মেলে। ঠিক আছে, আমি আজ অবধি যতগুলো পিপিটি আমি
Thank you,
পড়িয়েছি দেখে দেখে আমি পাঠিয়ে দিচ্ছি। ওকে, ইউ গো থ্রু অল দ্য স্লাইডস। ইফ এনি ডাউট এক্সিস্ট, কিন্তু এই পিপিটিটা শেষ হলো না, তো এই পিপিটিটা যতটা পড়িয়েছি অতটা দেখে রাখো, যদি কোনো ডাউট থাকে ইউ আস্ক মি টুমরো। ওকে, let me take your attendance.
ওকে ম্যাম।